Number 1, calculate the dot products. Okay, that's simple enough. A 137 minus 219. So 137 dot minus 219 minus 219 equals 1 times minus 2 plus 3 times 1 plus 7 times 9, which equals 3 minus 2 plus 64, which is 65. So there's our answer. B, 4 minus 1, 3 minus 4. 4 minus 1 dot 3 minus 4 equals 4 times 3 plus minus 1 times minus 4. That's 12 plus 4, so 16 our answer. Dot products of vectors yielding single numbers. Number 2, normalize the vectors. Alright, normalize the vectors. A minus 3, 4. So minus 3, 4 normalized equals minus 3, 4 divided by the length of minus 3, 4. The length of minus 3, 4 being the square root of minus 3 to the power of 2 plus 4 to the power of 2, 9 plus 16, which gives us minus 3 divided by the square root of 25 and 4 divided by the square root of 25, and then you can calculate out of that if you want to get an exact number. Doing this in a program, obviously you'd end up with an exact number, but giving this answer on a test, it's pretty much enough to have it like this. It's more human readable this way, but you can give the exact numbers. If you then have to take this vector and use it in calculations onwards into other transformations or matrices, then obviously you'd have to find an actual number that you can use in the rest of the calculations. But it's nice to keep it human readable as long as you can. So to B, normalize the vector 6, 9, 3. 6, 9, 3 normalized. Same thing, 6, 9, 3 divided by the length, 6, 9, 3, 6, 9, 3 divided by the square root of 36 plus 81 plus 9. And obviously you don't have to keep this kind of in one single chain. If you feel better just calculating the entire length first and then adding it into and dividing it into the vector, no big deal. So that would be 6 divided by square root of, we got 45, 126, 9 divided by the square root of 126, and 3 divided by the square root of 126. So we have the x, the y, and the z coordinates of this normalized vector. And what the normalized vector is simply it's a vector that has the exact same direction as this vector, but its length is exactly 1. So if you were to take these numbers to the power of 2 and add them up, you'd get 1. Alright, continuing. 3. Find the angles between the vectors 3, 4 and -12, 9. Angle between, right, this isn't great handwriting, but what you're going to do, 3, 4, -12, 9. 3, 4 and -12, 9. So what we do here when we're finding the angle is that we normalize the vectors first, and then we take the dot product of the two vectors, and that dot product gives us the cosine of the angle. So we can say cosine of the angle equals 3, 4 dot -12, 9 divided by the length of 3, 4 times the length of -12, 9. So I'm going to wait before I divide the lengths into this, before I normalize the vectors, because there's a possibility you can see from just the dot product what the angle is, or at least come close to it. In this case we have 3 times -12 plus 4 times 9. Okay, this will be divided by the same as the other side. Let's see where this leads us. 3 times -12 is -36 plus 4 times 9 is also 36 divided by, so what we end up here is 0 divided by the lengths of the vectors, and obviously the lengths of the vectors don't matter. Whatever we divide into 0, we're always going to get 0. So the cosine is 0, and thus if the cosine is 0, then we have the angle itself is 90 degrees. Okay, so we had two perpendicular vectors in that case, and so we can skip the part where we actually find their lengths and divide them that way. So 3b 175 minus 379. So angle between 175 and 379. Okay, so cosine of the angle is the dot product between them. So the dot product between them being 1 times 3 plus 7 times 7 plus 5 times 9 divided by their lengths, which are the square root of 1 plus 49 plus 25. Times the square root of 9, which is 3 to the power of 2, plus 49, which is 7 to the power of 2, plus 81. Okay, so let's see what we get here. So above the line we have 3 plus 49 plus 45. That gives us 45 plus 3, 48, 80, 97. 97 divided by, then we have the square root of 75 and the square root of 5766. And the reason I can multiply these square roots here is simply that each of them was a multiplication factor, that is 1 over each of them was a multiplication factor into the vectors where it took the dot product, and you can always take a scalar to a vector outside of the dot product. So I just take both of those scalars outside, I leave the dot product between the vectors, and I take the normalization just as the multiplication of these lengths. So the length of one of them is the square root of 75, the length of the other is the square root of 66. I divide both into the final dot product, and that should give me the number that I'm looking for. So let's just get a calculator up here. Like so. So we have 97 divided by 75 square root this divided by 66 square root. So this is 1. Let's look at it again. 1.379 is enough for us. 1.379. 1.379. Yeah. So this is the cosine. Then we should be able to say let's see if we have something more scientific. So 1.379. Is there a shift key or something here? Degrees. This is not what I was looking for. So it's clear. How do I get the arc cosine? Cosine of 0 is 1, obviously. Well, cosine of 0 should be 90 degrees. So what was that? No, obviously, no. The arc cosine of 0 should give me 90 degrees. So we're looking for... here's the shift key. I missed that. Clear. Alright. 1.379. Is not happy with that as the input into the arc cosine. Right, 0 arc cosine, 90 degrees. Great. Of course it's not happy with this input. This doesn't make any sense. So where did we go wrong? So the dot product of the normalized vectors should never be able to be bigger than 1. It should always be between -1 and 1. So what have we done incorrectly here? Okay, the dot product should be correct. Gives us 3. 5 times 9 is 45 plus 49. That's 90 plus 4 plus 3. That's 97. So we have the square root of 1 plus 49 plus 25. 9 plus 49 plus 81. Yeah, that'll be it. So this square root here should be like so. Alright, so 9 plus 49, we have 58. Yeah, I did just plus 8. Plus 81. So we have 58, 59, 139. That will give us 97. Take the shift key off, divided by 75 square root. Okay, that's the same as before, divided by 139 square root equals 0.95. Yeah, 0.95. That's nice. So okay, if the cosine equals that, then we can say 0.95 cosine, and the angle itself, angle equals 18.2 degrees. 2 degrees. Yeah, that would make sense. Seeing as we have the unit circle here, and we have a pretty high cosine, so it's way up here, meaning that we have a fairly small angle here. So that could make sense. Okay, moving on. Sorry about how long that took. Here. Number 4. Okay, here we should probably do a little drawing. So number 4. Yeah. We actually just erase this a bit more room, even though my whiteboard would end there, but just to make sure that we have plenty of room and we can clear this entirely. For the next one. So a surface has the normal vector 2, 3, 1. We'll draw this in 2 dimensions even though the problem in the end is in 3. So let's just draw a super simple drawing and not even think about what the actual numbers are. Let's say this is our normal vector n, and it equals 2, 3, minus 1. 3, minus 1. A particle traveling along the vector 1, minus 4, 1. And again, we're not even this vector, let's call it c equals 1, minus 4, 1. So this is nowhere close to being a correct image of these vectors. It hits the surface and bounces. And so we're supposed to do a reflection of this vector around the other vector. So again, in this very crude image, we're trying to find the vector r, which will be the reflected direction. And this is simple enough. We have the formula r equals, and you can find that in the recorded whiteboard session with intersections and reflections. If you go to that, you can also find a small PDF which just has the formulas written out, or you can go into the video, and in the beginning of the video the formulas are also simply written out. So r equals c minus 2 times C dot N times the vector n, and both of these need to be normalized. Or we can say C minus 2 times C dot n divided by the length of n squared, and the length of n squared is the same as saying n dot n times n. Okay, so this is what we're going to calculate. So in this case, r equals, what's our numbers there? 1 minus 4, 1 equals 1 minus 4, 1 minus 2 times dot product here on top, and dot product at the bottom, times 2, 3 minus 1, 2, 3 minus 1, which means that the top dot product is 1 times 2 plus, or rather minus 4 times 3 minus 1 times 1 divided by n dot n, that's 2 squared, 4, plus 3 squared, which is 9, plus 1 squared, which is 1. Okay, so continuing with this. R equals 1 minus 4, 1 minus 2 times, okay, so we have 2 minus 12, that's minus 10, and minus 1. That's minus 11, divided by 13, 14, times the vector 2, 3, minus 1. So if we put the minus 2 times and the minus 11 in here, we have R equals 1 minus 4, 1 plus 22 divided by 4, that's 5.5 plus 5.5 times 2, 3 minus 1. So R equals, now I can just take the whole thing together and say it'll be a vector where we have 1 plus 5.5 times 2 is 11. And the y coordinates will be minus 4 plus 3 times 5.5 is 16.5, 16.5, and the z coordinates will be 1 minus 5.5, and the yielding reflected direction equals 12 12.5 and minus 4.5. 12, 12.5 and minus 4.5. Minus 4.5. So that's our answer. Number 5. Following 2 points lie on a line. Give the point normal form for that line. Okay, minus 3, 2, and 1, minus 8. So we have points again. Okay, so it was minus 3. All right, let's have this bit to the side here. Minus 1, 2, 3. Minus 3, 2. 1, 2. So this would be one of the points. And the other point is 1, minus 8. 1, down 1, 2, 3, 4, 5, 6, 7, 8. Alright, so this is the other point. We have 2 points here lying on this line. 2, 3, 4, 5, 6, 7, 8. Here's the other point. And so we have a line going through these points. And the question is, give the point normal form for that line. Okay, so now we can just call this point here B. And it equals minus 3, 1. No, minus 3, 2. Minus 3, 2. We have this point here. Let's call it B2. And it equals 1 minus 8. And so we can say, let's make this vector first. We can call that the vector B or the vector C. Equals B2 minus B, which equals 1 minus minus 3, which is 1 plus 3. And minus 8 minus 2. So we have 4 and minus 10. Okay, this is the vector C, which is parallel to the line. Now I say the vector that we're interested in is in fact the vector N, which equals C perp, which equals, so we have 4 minus 10, then minus y, minus cy would give us 10, and cx would give us 4. So that's the vector N, but the point normal form in its entirety is we're asked to give the point normal form. Here we have the normal, it's 10, 4, so the point normal form would look like this. dot r minus, you can use either point, -3, 2 or 1, -8. We're kind of centering this around point B, so -3, 2 equals 0. So that's our point normal form, which is the answer to the question. Five B, the following 3 points lie in a plane. Give the point normal form for that plane. So we could draw up a picture and try to draw in 3 dimensions where these points lie, knowing that then what we need to do is to imagine they lie in a single plane, and we're trying to find the vector that is perpendicular to that plane. But it's simpler just to choose one of them, or choose them as A, B, and C, or P1, P2, and P3. Choose one of them to subtract from both of the others, and then we take the cross product of the 2 resulting vectors. So it doesn't really matter which ones we choose, but if we want more positive numbers, I think we can choose the middle one as the one to subtract from the others. So let's say that's 3, 5, 5. Let's just say we have the vector v1 equals 3, 5, 5 minus 4, 4, 1. Which equals 3 minus 4 is minus 1, 1, 4. Our vectors. That's our first vector, v2 equals 7, 6, 4, 7, 6, 4 minus 4, 4, 1, which equals 3, 2, 3. So these are our vectors. And then we can imagine, if we want to draw some kind of image, we can say v1 will look something like this, v2 will look something like this, where the points we were working with are the 4, 4, 1 point would be here, 3, 5, 5 here, and 7, 6, 4 over here. So okay, we have these vectors v1 and v2, and what we want now is to calculate a vector n, which is perpendicular to both of those vectors, like so. So the way to calculate that vector is by using a cross product. So n equals v1 cross v2 equals minus 1, 1, 4, 3, 2, 3, minus 1, 1, 4, cross 3, 2, 3. Okay, so the cross product, you can just look that up in the slides with the vector lecture. But in this case, it would look like this. So for the x coordinates in the resulting vector, we would take the y coordinates of the first vector and multiply with the z coordinates of the second vector. minus, and then we take the y coordinate or the z coordinates of the first vector, multiply those with the y coordinates of the second vector. Here we have what will be the x coordinates of this resulting vector. Then we just move one step ahead. So to make x we use y and z. To make y we use z and x in that order. So I kind of move like in a circle buffer and just go back to the start. So this will be 4 times 3 minus 1, so plus 1 times 3. 3 is both the x and the z coordinates of the vector v2. Okay, so here we have the y coordinates. The z coordinates will then be minus 1 times 2. We use the x coordinates of the first vectors times the y coordinates of the second one, minus the y coordinates of the first one times the x coordinates of the second one. And there we have our vector. So we'll calculate this. 3 minus 8 is minus 5. 4 times 3, 12, plus 3, 15. And minus 2 minus 3 is minus 5. So here's our normal vector, and that means we have to set up the point normal form, and we'll just pick one of these points to use. We'll use the 4, 4, 1 since we centered it kind of around that one. So 4, 4, 1 is the one we choose. So our point normal form will be minus 5, 15, 5 dot r minus, don't need that extra parenthesis here, was the one we're going to use, 441. 441. 4, 4, 1, like so. Equals 0. Okay, so there's our point normal form now. So this is a legit point normal form, but in a lot of cases where we're going to use it in graphics, we would like to normalize that normal vector. So finding a vector with the same direction but unit length will help us throughout a lot of calculations in the future. Otherwise, we'll have to make sure that we're dividing with the length of n in the correct places throughout the entire program. In some cases that's faster. In some cases it's faster to do it once and then send it normalized in and ask OpenGL not to have to normalize all of our vectors. So now we're at number 6. So a point normal form for a line in 2D or a plane in 3D is given by this condition. What we're going to check now is to see whether a point is at the front side or the back side of a line or a plane. And this might be of interest for us, number 1, for what's called back face culling when we're doing lighting in OpenGL or in graphics. We're not interested in drawing something, or well, when we're doing rendering in general, we're not interested in drawing something if it's part of an enclosed object, we're not interested in drawing the polygons that have the backside turned to us. So we can check whether our point of view, our camera, is at the front side or back side of a polygon in order to decide whether or not we're going to actually draw it. Also, in the case of collision detection, we might want to check whether, if we have an enclosed space, whether we're hitting the back side or the front side, just to see if it's actually possible to be hitting this surface at all. So the idea here is that we have the point P, and then we have the point normal form, line on a point normal form, where B is a point on the line, and N is a vector. So let's look at it something like this. We have the line, somewhere we have the point B, and then we have the normal N. And if we can imagine that the point P is on this side, this point P here would be at the front side of this plane, whereas if we have a point P here, we can call it P1, the point P1 in this case is at the back side. And the way we check this is simply if we can take a vector between B and P1, and we could actually, in this case, we could draw the vector N, the normal N here, although it doesn't matter where we're checking. We can take any point on the line, subtract that from, in this case, P1, and if this angle between them is obtuse, that is, it's bigger than 90 degrees, that means the point is at the backside. If, however, this angle is acute, less than 90 degrees, then the point is at the front side of the plane. And obviously, if the angle is exactly 90 degrees, then the point is actually on the plane or on the line. So this is what we're going to check. And we don't need to check the exact angle. All we need is a way to check whether it's acute or obtuse. So the first case that we have P equals 1, 2, and B is 3, 7. And N is minus 1, minus 4. So 1, 2, 3, 7. You can then say what we're looking for here is, wait, which one do we subtract from which one? Yeah, we take P, 1, 2, minus 3, 7. If we do it the other way around, we'll get the reverse answer, seeing as the vector would then turn the exact opposite direction. So we have to make sure this is correct. So we're doing P minus B, and we're taking that and saying the dot product of the difference between P and B, that is this vector here, the dot product of that and the vector N, and the vector N in this case is minus 1, minus 4, minus 1, minus 4, dot minus 1, minus 4, so that's dot N. This equals, so we can, this is a bit big here, but let's just move it a little bit to the side. We have 1 minus 3, that's minus 2, 2 minus 7, that's minus 5. Dot minus 1, minus 4. This equals minus 2 times 1, no, minus 2 times minus 1, this gives us 2, plus minus 5 times minus 4. Minus 5 times minus 4 is 20. Anyway, we get 22, and 22 is greater than 0. And if the dot product is greater than 0, that means the angle is less than 90 degrees. And if the angle is less than 90 degrees, angle is less than 90 degrees, means that P is at the front side. Okay, not great at writing on the screen here, but P is at the front side in this case. So, second one, do exactly the same. The only difference is it's in 3 dimensions. So we do minus 2, minus 1, 3, minus 2, minus 1, 3, minus, that's P minus B, 0, 0, 2, 0, 0, 2, dot N, which is 2, 7, 1, 7, 1. So that gives us minus 2, minus 1, 1, dot 2, 7, 1, which equals minus 2 times 2 is minus 4, plus minus 1 times 7, that's minus 7, plus 1 times 1, plus 2, that equals minus 4 minus 7 gives us minus 11 plus 2, that's minus 9. Either way, this is less than 0, which means the angle is greater than 90 degrees. So the angle is obtuse, meaning that, look at this again, obtuse angle means that P is at the back side of the plane. P at back side. Great. There. There. See if we can get a little room for examples here. So we have number 7. The particle is at the position A at time 0, traveling along the vector c, 1 full length of c per second. What is the particle's position at the time t when AC and t are the following? So the idea here is simply that we have the point, we have a point A, and it's traveling along a vector c, and so in 1 second the particle starts out there. It should be here at this point, which is the point A plus 1c. So A plus c is the point that's here. However, we have a different time, so we basically have to take a ratio of the vector c and add that to the point A to find out where this particle, which is moving along c, ends up. So A, we have 0, 0, 3, 5, and T1. So in the first case, we have 0, 0, plus, you can just say the position simply equals the point A plus the time t times the vector c, plus 1 times the vector c, which is 3, 5. So it just ends up exactly at the coordinates for c in this case, or the coordinates of A plus c. So in exactly 1 second, it should move exactly to the end of the vector c if we drew the vector c starting at A. So that's simply 3, 5. Simple enough in this case. So next part, we have minus 3, 5. So P equals minus 3, 5 plus the T is 3.5 plus 3.5 times the vector C, which is 2 minus 7. Which gives us 3.5 times 2 is 7. Add that to minus 3, gives us 4. 3.5 times minus 7 is 21, 24 and a half. So that's minus 24 and a half, which we add to 5, which gives us 19 and a half, minus 19 and a half, minus 19.5, like so. So that's our answer, second part. And finally the third one, C, 4 minus 7, 2. P equals 4 minus 7, 2. T is 0.02 plus 0.02, which is something that we can imagine is an actually normal frame time. So if we're working in frames, this would be running at 50 frames per second. So taking the vector that a particle should move along in a second, on 50 frames per second, we should take that vector, multiply it here with 0.02, and then add it to wherever the particle was in the previous frame. That means only a tiny amount will be added, so in the next frame after that, we again add 0.02 times that vector to wherever it was in the frame before, where we ended up with it. So this times minus 1, 3, minus 4, minus 1, 3, minus 4 yields 0.02 times minus 1 is obviously minus 0.02, so this will give us 3.98. 0.02 times 3 is 0.06, so we have minus 7 plus 0.06, So that'll give us minus 6.94. And finally, 0.02 times minus 4 is minus 0.08. So the final coordinate here, our z coordinate, will be 1.92. So that's our final result. Okay. Number 8. So here we're basically doing the same thing, except rather than setting up a point and a vector, we set up 2 points. And we say we have the point A and we have the point B. And so a particle starts off at the point A and it moves towards the point B in a straight line, and it should be at point A at t0, and it should be at point B at t1. And if we imagine that it just keeps moving in that same direction, the question is, where will it be at different times? And so there are 2 ways that we can do this. One way is to simply say, let's just make a vector here, the vector c, and we'll call that vector, or we'll calculate that vector simply by saying c equals b minus a, and then we can simply say p equals a plus t times c, same as in the previous example. Another thing we can do is that we can do what's called the linear interpolation. So we can say a linear interpolation between A and B at the time t equals one minus t times A plus t times B. So what we're doing here is basically taking a weighted average of the points A and B. We can see that at the time t equals 0, we get 1 minus 0 times A, which is 1A, and t times B, which is 0B. So we get no B, 1A, so we're exactly at the point A at the time 0. If we put in the time 1, we get 1 minus 1 times A, which is 0A, plus 1B, which is exactly B. So at t equals 0, we're at A. At t equals 1, we're at B. At any other time, we're at a weighted average of these points. And that would give us the same result. So in the first example here, we have A is 4.3. So we can start by saying, for the first one, we can do it both ways. Either start by saying C equals 1,5 minus 4,3. Which gives us minus 3, 2. And then after we've done that, we can say P equals A, which is 4.3, plus T, which is 0.6, 0.6, times the vector c, which we just calculated as minus 3, 2, which will give us, so 0, 6 times minus 3 is minus 1.8, so 4 minus 1.8 is 2.2, and then we have 0, 6 times 2, which is 1.2, 3 plus 1.2, 4.2. So this is one way of getting this. Another would be saying the linear interpolation would give us instead 1 minus 0.6 times 4.3 plus 0.6 times 1.5. So now we're not using the vector c, we're just using the points straight up, 4.3 and 1.5. And this gives, so 1 minus 0.6 is 0.4, 0.4 times 4 is 1.6, 1.6 plus 0.6 times 1, so that's 1.6 plus 0.6, which is 2.2. And the second one, 0.4 times 3 will give us 1.2, plus 0.6 times 5 will give us 3, so that's 3 plus 1.2, which is 4.2. Okay, this shouldn't be any surprise that we get the same result, but it's two different ways, either taking a weighted average of the 2 points themselves, or we make the vector and then we just do the same as we've done previously, which is moving it along the vector by the time t, or by the parameter t. So using the parametric form is one, doing a weighted average or a linear interpolation between the points is the other. Second example, so we have b minus a, let's just do it the same way here, c equals, b is 2 minus 3 minus 1, no, 3 minus 2 minus 1, 3 minus 2 minus 1, minus, no, that wasn't b, that was a. So b was 5, 1, 3. 5, 1, 3 minus a, which is 3 minus 2 minus 1. So let's just split this up. That gives us 2, 1 minus minus 2. 3 and 3 minus minus 1. 4. Then we have p equals a, which is 3 minus 2 minus 1, plus t, which is 1.2 in this case. 1.2 times the vector c, which is 2, 3, 4. So we have 3 plus 1.2 times 2 is 2.4, so 5.4, 5.4, 1.2, we have 3.6 on this side, minus 2, that's 1.6. have -1, and we have 4.8. That's 3.8. That's one way of doing it. The other way, we simply take time here, 1 minus 1.2. And of course the linear interpolation makes the most sense when we're using values for t between 0 and 1. But it'll hold true even outside of that. So here we're going to end up getting minus 0.2. And in the other case we'll get 1.2. But either way we're going to end up with a legitimate linear interpolation. So this times a, which is 3 minus 2 minus 1, plus 1.2 times b, which is 5, 1, 3. And this yields, so 1 minus 1.2 is minus 0.2. So minus 0.2 times 3 is minus 0.6. 1.2 times 5 is 6. So we have 6 minus 0.6, that's 5.4. Then we have minus 2 times minus 0.2, that's 0.4, plus 1.2, that's 1.6. And then finally we have minus 0.2 times minus 1, that's 0.2, plus 3 times 1.2, which is 3.6. That's 3.6 plus 0.2, 3.8. So same result in both cases, just different method. So number 9. In which point does the ray given here intersect with a plane with this point normal form? So here we already have formats of the ray and the plane set up for us conveniently, so we should just be able to go about setting up our t-hit and p-hit formulas. So t-hit equals n, normal to the plane, dot b minus a, difference between the point on the line and the point on the ray, divided by n dot c. So in our particular case, that would be our normal n here is minus 3 minus 1, 3. Times 3 minus 1, 3. Dot. So we can just calculate b minus a on the fly. 4 minus 1 is 3. 4 minus minus 1 is 5. And minus 2 minus 3 is minus 5. So we have 3 minus 3, 5 minus 5. 3, 5 minus 5. Divided by n, minus 3 minus 1, 3, dot, and the vector c from array 2, 3, minus 1. 2, 3, minus 1. So now simply have to solve this. So this equals, okay, minus 3 times 3. So we have minus 9, minus 5, we've got minus 14, minus 15. So minus 29. Minus 29 divided by minus 3 times 2. So we have minus 6, minus 3, that's minus 9, and minus 3 again, that's minus 12. Minus 12. So 29 by 12. Divided by 12 equals 2.427, just 2.42. Depends on how exact we want to be. 2.427. So this is our t-hit. However, the question here is, in which point does the ray intersect with the plane? So we need to continue, and we say p-hit, which is what we're actually looking for, equals a 1 minus 1, 3, minus 1, 3. We could actually, just to write this up completely, let's just say equals a plus t-hit times c, which equals 1 minus 1, 3, 1 minus 1, 3, plus t-hit is here, 2.427, 2.427 times c, which is 2, 3 minus 1, 2, 3 minus 1, which equals, let's just set this up nicely here, 1 plus 2.427, or we can just use this exact thing. Oh no, since we were already rounding it, let's use the rounded number, 2.427 times 2, 4.854, Okay, that's the first part. And we have minus 1 plus 3 times 2.427, 7281, 7281, and finally we have 3 plus, or scratch that, 3 minus 2.427, and so we have 5.854. We have 6.281, and we have 3 minus 2.427, that would be 0.573. 0.573, I believe. So here's our final answer. This is the point in which the lines given by this parametric form and this point normal form intersect. T hit first gives us the time, and then we use the time to find p hit. 10. So now we're going to take a single bigger problem of moving a particle in a certain direction, finding out where it hits something, reflecting it, and finding out where it is after a certain amount of time. And we're going to find a way to apply all of those methods, all of those vector mathematics that we've been looking at before, to solve this single problem. So to begin with, let's just draw a nice, well, a crude image of what we have here. So I'm going to look at the numbers here in the rectangle. Highest number on the x-axis is 9 and 8 on the y-axis. So let's set up a little coordinate system here. I think it's all in the positive quarter of this coordinate system. So if we take it about here, like so, 9 there, 1, 2, 3, 4, 5, 6, 7, 8, 9, and just about the same size of this here, 1, 2, 3, 4, 5, 6, 7, well, 8 up there. Okay, so the rectangle that we're looking at, 3, 1, and 1, 4, 1, 2, 3, 1 there, 1, 4 here, 9, 5 here, and finally what, 7, 8, 7, 8 up here. Okay, not a great image, but sort of gets the general gist of it. Okay, so we have a particle positioned at 1, 1. Call this point A. We can call this here P1, P2, P3, and P4 up here. And that particle is moving along the vector 1, 5. Should go like 1, 2, 3, 4, 5. So if we draw that starting at the particle, let's just mark the particle specifically and draw the vector here. That's more or less the vector. And we'll call that vector C. Vector C equals 1, 5. Okay, and the point A here equals 1, 1. So the idea here is to find this point here, its exact location, figure out when that happens, so how much of the time is left, and then continue along the new reflected vector for the amount of time that's left. And it states here, it asks at which position will the particle be at the time 1.0. So if it were uninterrupted, it would end up here at the time 1, since it's traveling along c for 1 full length of c per second. But what we're going to find out is where the intersection point is, and once we've figured that out, we're going to reflect it off of the correct side. So in the image we can see that it's the side between P1 and P2 that we're going to be looking at. But in a program we can't really see that, so we really need to go through calculations that'll make sure which side it is actually that we hit, which of these sides can we hit, which one is it that we hit, and at which time. So we'll go through a few methods that can help us with this. Since we see it on the image, let's just start with finding the actual point where it hits on the line between P1 and P2, and then we'll look at which methods we can use to eliminate the other sides. Okay, so yeah. Okay, so to begin with, we have this line here between P1 and P2, and we need to find a way to make that some kind of point normal form. So P1 equals 3, 1, 3, 1, P2 is 1, 4. So a vector between them, this vector here, let's just call that V. Say the vector V equals P2 minus P1. So that'll be 1 minus 3, which is the vector minus 2, and 4 minus 1, 3. So this is the vector V. Whoops. What we're interested in now is, so this is a vector that's parallel to the line that we're going to be looking at, but we want a vector that's perpendicular, so we're going to just say n equals v perp, which equals, if it's going that direction, alright, this vector would then be minus 3 minus 2. We could just as well decide that n is minus v perp if we'd rather use a vector with non-negative numbers. It doesn't matter which normal vector you use. So just for the ease of looking at this, let's do this like so. Okay, and say n equals minus v perp. Actually, we could just erase this as well. Like so. And equals minus v perp. Anyway, so we have a normal vector 3, 2 here, and we can draw that vector on the image as well. It'd be, if we're going to use for the point normal form the point P1, which is fine, we'll use this point here, and we'll use a vector that's 3, 2, which would look like this. So that's our vector n right there. So we're going to use the point P1, we're going to use the vector n, and for the ray we're going to use the point A, and we're going to use the vector C. So we can also say P1 now equals B. Same point, different name, just to use the formula that we have, which tells us T hit equals n dot B minus A. So we're using P1 as B, we're using the position of the particle as A, divided by n dot C, where C is the direction vector of the particle. Okay, so now we simply have to figure these things out. We can go up here and say b minus a, just to take that specifically. So p1, which is b, was 3, 1. So we can also say p1 is now b rather than p1. So b minus a equals 3.1 minus 1.1, which is 2, 0. So that's the vector between those points. So here we have n 3, 2 dot 2, 0 divided by 3, 2 dot, and our vector c was up here, 1, 5. Okay, so 3 times 2 is 6 plus 2 times 0, so that's simply 6. Here we have 3 times 1, which is 3, plus 2 times 5, that's 10 plus 3, that's 13. Okay, so 6 by 13. Let's just leave it at that. Okay, so now we found the time of hit here. So it happens at 6 by 13. So rather than actually calculate this for all the other lines, we can now do exactly the same thing for the line between P2 and P4, P1 and P3, P3 and P4. And we can do this for all of them. And then we can look at this T hit here. We don't have to calculate a P hit yet. Just look at the T hit of all of them. If we want to do this in a program, we do it for all 4 lines. We check the T hit and we take the T hit that's lowest but still positive. A negative T hit, for instance, if we look at our picture, when we take the line we've already taken here, we're going to get a positive T hit. When we take this line, we're also going to get a positive T hit. And judging from the picture, it's also going to be somewhere between 0 and 1, so it's within our range. However, the one we've already found is smaller, so that's the one we're interested in. When we take this line here, we're going to find a hit point that's somewhere up there. And it'll have a positive T hit, but it'll be way bigger than the other two, so that's not what we're interested in. When we take this line here, however, we're going to find a T hit that happens somewhere down here. It'll be a negative T hit, so that's something we're not interested in either. Also, when we do this in a program, once we've actually found a T hit that we're interested in, we now also have to check if that T hit actually happens between the points P1 and P2. So if it happens between the points P1 and P2, then we take the smallest of those and choose that. So we do the T hits. Anytime we find a T hit that's within the range that we're looking at, we'll calculate the P hit, see if it's actually between 2 points, and continue from then on. So now we know this is going to be the lowest T hit. We're going to calculate P hit now, and we're going to set up a little check to see if it's actually between the 2 lines. So we have T hit there. Next is P hit. So P hit is just the formula for the array, the parametric form of array, A plus T hit times C, using the value of T hit. So in our case, this gives us A was 1.1, T hit was 6 by 13, times C, which was 1, 5. 1, 5, 1, 1. Okay. So let's see what we get here. That gives us 1 and 6/13. And then it gives us 1 plus 5 times 6/13. That's 30/13, which is 2. So we have 1, we get 3 and 4/13. Okay, so 1 and 6/13, 3 and 4/13. So that's the hit point that we have. So now we check. Now we check if P hit is between the line segment ends. And all we need to do is just check if either the y or the x values are in between. So let's just look at the x values now. So the x value for P1 is 3, the x value for P2 is 1. So we just need to see, is 1 being P2x smaller than P hit x, which is 1 and 6/13, which is smaller than P1x, which was 3. Okay, so this is true. Which gives us basically a positive check here. So that's nice. Now we know that the point is actually between or inside the line segment. So all of this is good. And now we know that we're actually hitting in the spot. What we need to do now, we've actually found the point as well, so we know where it hits. Now we just need a new direction for A. Since the old direction for A hit here, we need to say, okay, now we're going to take this normal here n and imagine that it's here. It doesn't really matter in which direction this n turns. We could imagine if we have the other way around, it's here. And then we take A and we're going to say we need to find the reflected direction where this angle and this angle are the same, and this will be our new vector. We'll call it R here, but that's the new vector for A. It'll be our new C. So now I have to find that vector, and once we found it, we're going to take the amount that's left of t from the time we started until the time we want to end. In our case, that's the time 1. In many cases, it'll be the total frame time. We'll subtract from that the t hit, which we've already traveled, and so say what's left of it is then what we have yet to travel. Alright, so we have a formula for this. So right now we found the point where we hit, and it doesn't really matter where that is for the reflected direction. The only thing that matters is the normal that we have, normal n. So our normal n is 3, 2. However, we are going to have to normalize that or divide by its length. So the formula that we have here for the reflected direction looks like this. R equals A, which in our case is C, minus 2 times a dot n times n, which is the vector, if n is normalized. However, we can say this divided by n dot n will add the normalization into the formula as we go. Since we have a non-normalized n now, we'd have to add that. So this is the length of n squared, and since we have two instances of n here, then we can divide by the length squared to normalize both of those as we go. So in our case, this would be r equals, so a is c, the vector a equals c, which equals 1, 5, n equals 3, 2, and that's all we need. So we have 1, 5 minus 2 times 1, 5 dot 3, 2 divided by 3, 2 dot 3, 2 times the vector 3, 2. This gives us 1, 5 minus 2 times, 1 times 3 plus 5 times 2, that's 13. We already had that dot product earlier. So then we have 9 plus 4, which happily also gives us 13, interestingly enough, times the vector 3, 2. So this equals 1, 5 minus, so we have 2 times 13 by 13 is just 1, so minus 6, 4, if we just multiply 2 into this set here. Alright, that gives us the vector minus 5, 1. So let's look at how that looks on our image. Minus 5, 1. We have 1, 5. And minus 5, 1. Yeah, that's more or less. Minus 5 in this direction, we don't have room for that. But if we go like back about 2.5 and then up 1/2, it seems like it could be the right direction. So let's use that. It's correct enough. Let's see, back to the old drawing board. Okay, so that's the vector we're going to use. So we're going to say minus 5, 1 is the new direction. So the particle that we have the point A. It needs to take its whole direction, which is here, vector c, but it needs to do that. It needs to travel this vector here, which is c times t hit. Then it needs to change directions and say the new vector is now this vector here. That was too thick. This vector here, which is now the new vector c. We can just call it c new. But it has to travel that vector So C new times 1 minus T hit, which is the rest. Or, as I said before, in the case of using the frame time, it will not be 1 minus T hit, but frame time minus T hit, or delta time minus T hit. So we know that after traveling C times T hit, it'll be at the hit point. We've already calculated that. It's here. 1 16/13, 3 and 4/13. We have 1 and 6/13, 3 and 4/13. So now we have to travel from there. So that's our new A. This is kind of our new A, or our temporary A. So A moves to here first, and then we add the other vector. And in the program, once we've moved A to here, then we actually change the value of A to that, and change the value of A's traveling vector to the new vector. And the old traveling vector doesn't matter anymore because it's already reflected. Okay. There. So finally, we now have 1 and 6/13, 3 and 4/13. That's our new A. So the final A, call it A S for solution, equals this intermediate A plus 1 minus T hit. And 1 minus T hit is 1 minus, where was T hit again here? 6/13, so what's left of that is 7/13 plus plus 7/13, and we can just mark that here with 1 minus T hit. Seven thirteenths times the new vector, which is minus 5, 1. Minus 5, 1. So this gives us the final answer of 7 times 5 is 35. Not plus, but equals. So we have 35 by 13, which is 13 would give us 39, so it's 2, it's minus 2, it's 26, so there's 9 off of that, minus 2 and 9/13, and 7 by 13. So this is our final answer. This is the position of the particle after it's traveled for 1 second, and inside that 1 second reflected off of this line here. So it said it was, no, this is not correct, sorry, we forgot to actually add the point itself. I'm gonna erase this. What we need to have here is, okay, so this equals 1 and 6/13, 3 and 4/13, plus what we had earlier, which was -2 and 9/13 and 7/13. So this is what's being added. This is where we were at. This gives us, however, okay, 9/13 subtracted from 6/13. That's okay. That's so we have 10/13 left. -2. So that's -1 and 3/13. And then we have 3 and 4/13 plus 7/13. 4 plus 7 is 11. So that would be 3 and 11/13. Okay, so this is our final position, and now we can look at it on the image and see if that makes sense. So -1 is 3/13. It's just beyond the picture here. And then 1, 2, 3 and 11/13. I guess it's not far off. It ends up somewhere around here. If we did any wrong calculations, it doesn't matter because we did the method correctly. If we dropped a minus somewhere or a single 13th, that's okay. So one more thing that is nice to look at here. So this is the answer to the question, that's fine. But one more way that we could have to eliminate some of these sides is that if we make sure that when we make the normal vector for each side, the normal vector is pointing out from the box. Not into the box, but out from the box. In that case, we can actually say we can take a vector from any point on the line. So take a vector from P1 to A and the normal vector, and we can check the angle between them. If that angle is acute, and we don't even need to check the entire angle, we just need to take the dot product, and if the dot product is bigger than 1, that means we have an acute angle, and that means that the point is at the front side, so it's outside the box. And that means that we could actually hit. If we look at all of the other ones here, you can see that this normal here and a vector to A would give us an obtuse angle, an angle that's bigger than 90 degrees. That simply means that we get a dot product of less than 0, a negative dot product. A negative dot product between these vectors tells us that A is actually on the other side of this, on the back side of this side, meaning that if it were to hit this side, it would be hitting from the inside. And if we have an enclosed box, we can say we're never going to be interested in hits from the inside. So if we begin by taking each of these lines in this way, we can look at it a bit clearer here with this line where we haven't drawn so much. So we take this line here, we take its normal here, n, and we take a vector all the way to where we're checking, A here. We take the dot product of these two vectors, it gives us minus, so we can see, okay, if this were to hit from any direction, it doesn't matter where it's traveling, the hit would always happen on the back side of this polygon, and we're not interested in that. This one as well. So in this particular case, if we would start by with that check, we could eliminate this side, and this side, only having to check this side. The way we do it now, instead we check all the sides, we find T hits. We're going to find this side anyway, because it has the lowest T hit, but we could eliminate it beforehand in the other way. Just bear that in mind. So here's our final answer.